In this video, I'm going to solve this differential equation. By looking at the differential equation, it kind of looks like an exact differential equation that has the following format: P of x comma y dx plus Q of x comma y dy is equal to 0, where P of x comma y is this and Q of x comma y is this. Now, in order to show that this is an exact differential equation, we need to do the following. We need to show that del P over del Y is actually equal to del Q over del X. Now, del P over del Y is del over del Y of 6x squared minus 2y plus 1. And if I take the derivative of it with respect to y, I get just negative 2, because derivative of 6x squared is 0 with respect to y and derivative of 1 is 0 with respect to y. So del p over del y is negative 2. And let's see what I get for del q over del x, which is del over del x of 3y squared minus 2x minus 3, and derivative of 3y squared with respect to x is 0, derivative of negative 3 with respect to x is 0, derivative of negative 2x with respect to x is negative 2. So we just showed that del p over del y is equal to del q over del x equal to negative 2. Both of them are equal. So this equation is in essence an exact differential equation. So we can go ahead and solve this exact differential equation. If you have an exact differential equation you're trying to solve, the general answer format is going to be f of x comma y is equal to some arbitrary constant c. Now, how do we go about finding the solution to this f of x comma y? It's not too hard. We know that p of xy, okay, p of xy is nothing but derivative of f, partial derivative of f with respect to x. So we have del f over del x, right, is equal to p of xy, p of x comma y, and that is equal to 6x squared. So this guy, 6x squared minus 2y plus 1. Now I can integrate it with respect to x, integrate it with respect to x, and integrate this whole thing with respect to x. If I integrate del f over del x with respect to x, that actually gives me the original function f of x comma y. And integral of 6x squared with respect to x is going to be 6 times x cubed over 3 minus 2y. Integral of that with respect to x is 2y times x, plus integral of 1 dx is just x. Now I have to add a function of y, let's call it g of y, and that kind of serves as a constant in a way, because we are integrating with respect to x. So now let's go ahead and rewrite it. F of x comma y is equal to 3 goes into 6 twice, so it's going to give me 2x cubed minus this is going to give me 2xy plus the x and then plus the g of y. So for our purposes we kind of found the f of xy, except that f of x comma y, except that we didn't find g of y. How can we find g of y? Is there a way to find g of y? The answer is yes, you can find a g of y. You know that q of xy, which is this guy, is actually partial derivative of this function with respect to y. So del f over del y is gonna be equal to, so derivative of this with respect to y is 0, derivative of this with respect to y is just negative 2x, and derivative of x is 0 with respect to y, and derivative of g of y with respect to y is g prime of y. So this must be equal to q of xy, which is 3y squared minus 2x minus 3. So I can add 2x to both sides. That's going to give me g prime of y, or derivative of g with respect to y, is equal to 3y squared minus 3. Then I can go ahead and integrate both sides. G prime of y dy is going to be integral of this thing, which is going to be 3 integral y square dy minus 3 integral dy. And g prime of y, if we integrate it with respect to y, that is going to give me g of y, right? So g of y is equal to 3 times integral of y square is y cube over 3 minus 3 times integral of dy is just y. 3 cancel out. That gives me g of y is equal to y cube minus 3y. Now I can take this g of y and plug it in right here. If I did that, I'm going to get f of x comma y is equal to 2x cube minus 2xy plus g of y. But g of y is y cube minus 3y. And that, by the way, must be equal to some arbitrary constant c. And this is the solution to the differential equation that we were trying to solve. I hope that this discussion was helpful. Thank you very much.